For this last example, we're going to switch it up a little bit and use a trig equation, okay? So a lighthouse that's 1 mile offshore has a beam which rotates at 3 rotations per minute. How fast is the beam traveling along the shoreline when it is 5 miles downshore? And this is definitely one that we need to have a picture to understand what's happening, okay? So I'm going to draw this. I'm going to draw this with the lighthouse right here, okay, somewhere out 1 mile offshore, and then the shoreline is going to be right here. So this distance is 1 mile, okay, and then here's the shoreline, and we have a beam of light that is rotating around this lighthouse at 3 rotations per minute. Now we are going to need to convert that, but rotations per minute, remember 1 full rotation is 2 pi radians, so 3 rotations per minute is equal to 6 pi radians per minute. Okay? All right. Now, how fast is the beam traveling along the shoreline when it is 5 miles downshore? So this is the instant when it is 5 miles downshore. So I'm not going to label that on the picture, but I do need a point for where the beam of light is. So here's the beam of light, and go ahead and draw this. Okay, so the beam of light is traveling from the lighthouse and it is hitting the shore. Again, the instant is 5 miles, but I'm not going to label this distance with 5 because that is not a constant value. So instead, I'm going to use a variable, and I'm going to use a y just because this is vertical. You can use x, you can use b for beam, it doesn't really matter. Okay, so I have the right triangle. Okay, and I also know that the light beam is rotating at 6 radians per minute. That is the rate of change of this angle right here. I'm going to call that theta. Okay, you can use a different variable for the angle if you would prefer. But here we're not talking about the length of the beam of light because that doesn't really make sense in the context of this. What we are talking about is how fast this angle right here is changing. Okay, so we are given that the rate of change of this angle, or in other words, d theta over dt, is equal to 6 pi radians per minute. And then we are looking for the speed that the beam of light is moving down the shore. So we're looking for the rate of change of this distance, or in other words, dy over dt. Okay, and that's going to be something in miles per minute. I know it's miles per minute because we're measuring distance here in miles, and this is spinning in something per minute. Okay, so step 3, what is the equation that relates these variables? It's going to be a trig function. Okay, we're going to use tangent. So tangent of theta is equal to y over 1, which is just y. All right, now once we have that equation, we can differentiate with respect to t. Okay, so we get secant squared theta times d theta over dt is equal to 1 times dy over dt. All right, and now we're plugging values in given our instant. Okay, once you've taken the derivative, then you can use the values for your instant. So dy over dt is what we are solving for. D theta over dt is 6 pi. We need to know what secant squared of theta is at this particular instance. So let me draw another triangle. Okay, and we are looking for secant squared of theta when this distance is 5. And remember, this distance is a constant 1. So secant of this is hypotenuse over adjacent, or 1 over cosine. Pythagorean theorem tells me that this is root 26. So secant of theta is root 26 over 1, or just root 26, meaning that secant squared of theta is root 26 squared, so 26. So I have 26 times 6 pi is equal to dy over dt, which I'm going to go ahead and plug that into a calculator, and that comes out to be about 490 miles per minute.